All right, what's going on, guys? So in our previous presentation, or sorry, my previous presentation, this previous tutorial, what we did was we actually showed our loss and accuracy by implementing, I think we might have finished the compute loss function and we finished the compute accuracy function. And pretty much what it did was for every feed forward that we have going in, we sort of tested it against our values for y, which are our y true. And we sort of said, okay, given these outputs here, how many of them are actually coincide with our y true values and compute that accuracy and return it, right? So in our previous presentation, previous tutorial, I had done all that. We noticed that the loss does go down, so our model is still learning and has the capacity to learn. Our accuracy can't get much better because that's sort of the limitation um, of our simplified model of 2 features and 4 training examples. There's not much more to be had. But what we can do actually is play around with the models and the tunable parameters a bit, just so that we can really get a model that drives these two, the extremes, the ones and the zeros, which is our y true answers. So one of the things that's nice to look at is it'd be good to look at the losses, right, over time. So we know that we're actually looking at the loss here. So we actually compute it. So we could actually just grab our loss. And so much so that we're actually going to have one for accuracy too, okay? So we're going to set those as empty lists. And then after this is computed as ls. I sort of want to do it here. Okay, you obviously cannot call it the same thing. You cannot call that the same thing. So loss and accuracy are those empty lists. Our loss is going to be just loss.append ls, so that every iteration is just going to append it to loss. And over here, we compute loss here at only, if we have 1,000 epochs, it only does it every 100 by this divided by 10. But let's just say we wanted to compute the loss every iteration, just so we can plot it, okay? So we can do the same thing where, we take the accuracy and we're going to append. What we're going to do is we're going to append the accuracy here, plop it down there, okay? Just so we don't run it twice, okay? So we're going to compute the accuracy, store it as accuracy, append accuracy here, and print it so that we can see it as the model continues on right here, okay? Of course, you could just take this and put it down there, but I just didn't want to compute it twice, okay? So let's do the same thing. Okay, so this model, again, our model is a little too reliant on the initializing weights and biases because I ran it for 1,000 epochs this time. And what happened exactly? Well, the accuracy actually did not breach 0.75, right? Which is not what we want. But we do want to, but what we do want to do, let's just make sure that's right. Yeah, so what we do want to do is we sort of want to plot, okay? So at the top here, we're going to import matplot.pyplot as plt. That's right. Okay. Okay, so that we can do plt plot dot. Okay, this is turning red because something. Matplot lib. I actually don't know why that's red. Anyway, so we're going to plot our loss. Okay, so let's just see what that loss looks like over time. Looks like nothing because we called it the wrong thing. So we'll see what that looks like. Okay, so we can sort of see at this point, this is where the model was really, it's always good to look at what those final outputs look like. just so we can see exactly what our model is showing, okay? Okay, so it's saying at this point, the loss, it sort of became saturated. Our accuracy is only 7.5 because this guy, for whatever reason, is not being driven higher. It needs to be above 0.5 for this last y true statement, or y true to be true. So that's the loss. Let's just plot quickly the, I think we're going to make things easy for us. And we're just going to, it's sort of nice to plot these on the same one. So what I'm going to do is take that plt.plot. We're actually going to plot that on the first axis of our subplot. And then we want to plot it on the axt.ax1.twin. So what this is in fact doing is it's just copying the same axis from ax1, twinning it so that we can take ax2 and plot the second one and overlap. That's what we want to do. And we called it accuracy up there, so we call it accuracy down here. Let's see if that works. ax2 is not defined. And we want a twin x for twin axes. Okay, let's make things easier for us. And let's make that red, make that blue. I know we can play around with the axes labels, but we sort of know what we're doing here. So this is our accuracy. So at this model, we actually got decreased accuracy, went back up, and came to 100% about there, but there's still a lot of training to be had here. So let's look at our model again and see that, number of epochs, how much would changing that change things? Like, are we really learning anything? Let's see. So it looks like we are. Okay. So look at this loss. So we actually, it's kind of hard to see because, so what we could do is actually just plot it down here again, only because I want to see what these, this last little bit looks like. So we can just say, let's look at the last 500 or so elements. Okay. Again, this is accuracy is the blue, this is the loss. You can see that there is a lot of learning to be done, right? So we actually did not exhaust our learning capabilities. And let's take a look up here. Remember, this is our feed forward. These are our guesses after 5,000 epochs. You can see how close this is driven to 1, right? It's almost fairly, let's just say 95% sure this is a 1. These are being driven close to 0, and this is being driven close to 1. 1001, fantastic, okay? So there's actually not much to be done here. What we could do is we could lower this. Let's just add some, add a lot of capacity just to see those being driven right to 0, or the loss being driven practically to 0. And again, there's still a lot of training to be done. Let's grab the last 500. This is still learning, right? Even at the last 500 epochs. Again, being driven to 1, 0, 0, 0. But there's still a lot of learning to be had, like I said. So let's just, one final time, for all fun's sake, let's just do that. And we can leave the learning rate because there is still a bit of learning here. It's not like we're being saturated in our learning, right? So more epochs is still helping us. Run that. Okay, and it seems like we're sort of becoming saturated, and it's not helping too much. Look at the last 500. And again, it seems it's learning, but again, look at these, we're getting fooled by the y-axis because it looks like we're learning, but I mean, not too much. I mean, this is practically, loss is practically 0. So there you go. We developed a successful model. We showed with our loss and accuracy that our model is learning. We can actually see that by increasing things like capacity, we can sort of fine tune it a little more, but at some point, we're becoming saturated. Our learning is becoming saturated. And if we had another, if we had a real life model where we have a training and we have a validation, being 100% accurate is not what you want, and low accuracy or low loss on just the training examples, it's not the best. But for this model, our training and validation is one of the same. This is um, just for learning. So it seems like for the next presentation, what we're going to do is we sort of limit ourselves in that our model is, for the most part, very modular. Um, it would have been great if perhaps, what if instead of doing a 100 by 100 model, a 10 by 10 by 10 model would run properly, right? So this is running properly because an architecture is only looking at the first two. But what if we wanted to expand this, right? Well, if you look at our class, and the methods within our class, you'll see that we modularized everything, right? 0, 1, 1, 1. Everything is modularized, or is not modularized. And the problem with this is we actually could not expand this architecture because we didn't do it here, and here we didn't do it either, right? So if we wanted to add 4, 5, 6 more hidden layers, we'd have to do that by hand, which is not good programming practice. Same here, it's not good programming practice. So for the next presentation, I think we're going to modularize this, make it a little easier us to expand our ANN to any sort of hidden layers that we want. And perhaps we'll play around with the learning rate and this architecture a little more to see if we can reduce the number of these neurons required to train our model to perform at 100% accuracy. So with that, we'll see you guys next time.